Okay, welcome. We'll get started in just a second here. We're going to be continuing on where we left off there, talking about gases and gas laws. So again, we should be into chapter 7 here, kind of finishing up the gas law part of it. Then we'll continue on. As usual, make sure if you do have any questions that you do ask below in the chat. And again, we'll get to your questions even if we happen to be sort of past it at that point. Okay, so why don't we get started? So we've been talking about gases and gas laws. Remember that you are responsible to know the different gas laws. We've come across a number of them at this point. Um, let's see, maybe we go back one here. Remember, we talked about basically Boyle's law, which is the relationship between pressure and volume. Pressure P1 V1 equals P2 V2. That's at constant temperature. We also saw Charles' law, which is V1 over T1 equals V2 over T2. That's at constant temperature. I'm sorry, constant pressure. Remember that when we do have gas laws, pretty safe bet that if you do have temperature involved, like in Charles' law, for example, that you do need to convert to temperature into Kelvin. So we would want to make sure that we add 273 to the Celsius. Volumes doesn't matter as long as they're the same. We also saw Guy-Lussac's law, which is P1 over T1 equals P2 over T2. Again, here the temperature needs to be in Kelvin. The pressure could be any unit as long as they're the same on both sides. And again, that would be at constant volume. We also saw Avogadro's law, which is V1 over N1 equals V2 over N2, V being volume, N being moles. Again, that would be at constant pressure and temperatures when Avogadro's law kicks into place. We also saw putting those together, which is the ideal gas law. That's the PV equals nRT. Remember, out of all of them, the ideal gas law is sort of the most restricted in terms of units. You can take pressure has to be in atmospheres, volume has to be in liters, temperature still has to be in Kelvin, and needs to be in moles. And R is a constant, which is 0.08206. And again, it's different in the sense that it is only sort of one set of conditions. So unlike all the other ones, there's no before and after. You just have one pressure, one volume, one temperature. But it is the most restrictive in terms of units. So you got to make sure everybody's converted to the right units before you use the ideal gas law. If you're not sure what those units are, again, you can look at R, which is usually given to you. And R, all the units that are associated with R, those are pretty much all the units that everybody else has to be in. So R in terms of pressures, atmospheres, L, liters, moles, and Kelvin. So you can kind of use R to sort of figure it out as well. I think we finished up talking about at the end there a couple of things. We also talked about STP. Remember that STP is standard temperature and pressure. And when you are given something at STP, it actually does stand for a value. So the temperature at STP is 273 Kelvin. The pressure at STP is 1 atmosphere. So a lot of times the problems will just give you STP, and you're supposed to know again that it is 1 atmosphere for the pressure, 273 for the temperature. And there was a relationship that occurs again only at STP conditions. So only at STP conditions, if you have 1 mole of any gas, it equals 22.414 liters. So that's a conversion factor that you could use. Again, as we talked about last time, that is specifically for STP conditions, which means if the temperature is not 273 and the pressure is not 1 atmosphere, then you can't use that relationship. You do have to use the ideal gas law. So as we talked about, you can use the ideal gas law under any conditions, STP conditions, non-STP conditions. But that conversion factor that we saw the other day, 1 mole equals 22.414, is only at STP conditions when you can use that. So make sure you don't use it in all conditions. It's got to be specifically just those STP conditions. We finished up, I think, talking about one last gas law there, which was referred to as a combined gas law. That's P1 V1 over T1 equals P2 V2 over T2. That's the one where pretty much all the sort of variables come into play together: pressure, volume, and temperature, and we're changing one of those 3 variables and how they affect the others. Again, we also talked about in a lot of those gas laws sort of the relationship that occurs, for example, in Boyle's law, pressure goes up, volume goes down, and vice versa. Again, those are good things to know because that will help you when you do the math part, make sure your answer sort of makes sense. Any questions on any of that stuff we talked about sort of last time? Okay, so I believe this is where we left off. So we're not going to talk about Dalton's law of partial pressures, which sounds very difficult, but it's sort of a basic sort of concept. So if we have a gas and the only gas molecule, for example, in here is gas A, the total pressure associated with this mixture would be the pressure of gas A, as it's the only gas that's basically flying around. So only gas causing collisions. Remember, as the rates of collisions increase, so does the pressure that we associate with it. But if we take sort of that same container, and in that same container, we don't have just gas molecule A flying around in there, but maybe we got gas molecule B flying around with it. The total pressure of this is now a mixture of those gases and is a result of the pressure of A plus the pressure of B, as they are both basically contributing to the overall pressure in that mixture. So as A is flying around and causing collisions, as B is flying around and causing collisions, they are both causing basically pressure that's associated with that mixture of gases. And these are what are referred to as partial pressures. So when we talk about this guy, P of A and P of B, these are what are referred to as partial pressures. And they're partial pressures because they each contribute to the overall pressure in that mixture. So how do we get those pressures? So there's really 2 sort of common ways that you could get the partial pressure of each gas in that mixture. The most common way is to use our ideal gas law, our PV equals nRT. And here we would solve for P, which is nRT divided by V. And we would solve for P for each gas individually. So although they are flying around in the same container, we do sort of assume, and sort of one of the ideas of sort of the ideal gas situation is, although there's multiple gases, different gases flying around in the same container, they pretty much will have no effect on each other as they're flying around. So it's sort of an ideal situation, and the pressure of one will not really have necessarily an effect on the pressure of the other as they're flying around or perhaps colliding with each other. So we would take each gas and almost treat them separately as they were in there by themselves, and we would use the ideal gas law and solve for P for each gas. Now, the good news is that since they are in the same container, there's a couple of things that are the same for every gas that you have in there, 2 gases, 3 gases, because they're flying around in the same container The volume is the same for everybody, and so is the temperature. So the volume and temp are the same for each gas. And that means in most cases, when you do sort of a partial pressure problem, the only thing that you really need to figure out for the most part is the number of moles of each gas. So you can figure out the number of moles of each gas. And that's really the only thing that's usually different. Again, R is a constant, which is that 0.08206 number, and V and T will be pretty much the same for every gas. Again, since it is technically the ideal gas law, you do want to make sure that everybody's in the correct units. So again, temperature needs to be in Kelvin, volume needs to be in liters, R is obviously a constant, and N needs to be in moles. And that's really what Dalton's law of partial pressures are. The total pressure of the mixture is simply just adding together each of the partial pressures of each gas in that particular mixture. So you would essentially do the ideal gas law for each one separately. And then to get the total pressure, you would essentially just add up all the individual partial pressures, and that'll get you your total pressure. Any questions on that there? So like I said, using the ideal gas law is typically the sort of method that we use. Another method would be if they just gave you sort of the partial pressures of each gas, or they gave you the total pressure and one of the partial pressures. If it was a mixture of two gases, then you could again use this relationship here, that the total pressure equals the pressure of each gas. So a variation would be they may give you the total pressure, may give you one or more of the partial pressures. And for example, if that was the case, you could rearrange this and solve for the other guy and basically just subtract. So if they sort of give you the partial pressures, you could use that relationship that you just need to add up all the pressures together to get the total pressure, and then you can kind of rearrange it. But again, commonly you do have to usually use the ideal gas law for each of the gases there. All right, so you have an example. So why don't you take a couple of minutes here and give it a go. We're looking for the partial pressures of each of these gases, and we're also looking for the total pressure when it's all said and done. Let me give you some information that you might need. Helium from the periodic table, 4.003 grams per mole. And what we got there, neon, I think. Okay, sorry, other gas. Neon is 20.18 grams per mole. All right. So why don't you take a couple of minutes there and see what you come up with. You should have three answers, two partial pressures, and then a total pressure. So take a minute or two, and then we'll talk about it. Okay, so let us take a look and see how we're doing here. So again, we have basically a mixture of two gases. So we got helium flying around in that container. Oops, come back. There we go. We have, if we look at that container, we got helium in there. We got neon flying around. And again, they're both going to contribute basically to the total pressure in this mixture. So we need to find the pressure of each of those. So again, in this case, we are going to use PV equals nRT. And remember that if we kind of go through it, we do have the volume, which is the same for everybody since they're in the same container. We also have the temperature, which is 27 degrees, which is going to be the same for everybody in that container. We have R, which is a constant. So again, we always have R, which is the 0.08206. Come on. Grab an eraser here. Oops. Try that again. See if it's any better. 0.8206 liters times atmosphere, Kelvin times mole. And that means that we do need to solve for P for each of them. So we're going to rearrange that. P is going to be nRT over V. So really the only thing that we're missing when we kind of look at sort of the ideal gas law again is moles. And we're not given moles in this case, but we are given grams. So we can go from grams to moles using the molar mass from the periodic table. So that would be the first place where we want to start. We would want to start with converting our grams into moles. So the first part of this would be to figure out the moles of each of those gases. And again, those numbers come from the periodic table, the 4.003, which is the molar mass of helium, and the 20.18, which is the molar mass of neon. And now, since we do have the moles of each gas, we can get the pressure of each gas, or the partial pressures of each gas, by using that ideal gas law. Now we're just going to do the calculation for each gas separately. So in this case, for our first gas, we're going to take all of our numbers in there. So this is our N, which we got from above. This is our R. Again, sometimes people use this rounded version of the number. This is our T, which is converted to Kelvin, which is 300 Kelvin. And this is our V down here, which is the 2.50 liters. All the units are going to cancel. The only unit that won't cancel is the atmospheres. Again, the moles here will cancel. Kelvin will cancel. Missed it. Liters will cancel. And again, the atmosphere is the only one left over. And if we do it there for helium, we get 12.3 atmospheres. 12.3 atmospheres would represent the partial pressure of helium. So this is the partial pressure of helium. Any questions on that calculation there? For our other gas, we're essentially going to be doing the exact same calculation. Really, the only thing here that's going to change is we're going to use the moles of neon instead of the moles of helium. And if we put that in, again, we have our N, which in this case is 0.248 for our neon, our R, which is our constant, our temperature, again, still 300 Kelvin since they're sitting in the same container, and our volume also 2.5 liters because they're sitting in the same container. And if we do that for neon, put in all those numbers, we will get 2.44 atmospheres. Again, that is what is known as the partial pressure in this case of neon. Right? So that's the partial pressure of neon. Any questions so far? So those are two of the answers that we're looking for. The third answer that we're looking for is essentially the total pressure. So the total pressure is basically just taking each of the partial pressures and simply adding them together. So in this case, we would take the 12.3 and we would add it to the 2.44. And that would give us our total pressure down here of 14.7 atmospheres. So that's a very common sort of way to figure out partial pressures. It really is just an ideal gas law. Again, the importance of the ideal gas law, as we talked about before, is the units. You want to make sure everybody's in the correct units before you put it into the ideal gas law. Otherwise, again, you'll get the wrong answer. And then you simply would just add together all the partial pressures to get it. Now, we could also see from the pressures here that the major contributor to the pressure in this mixture is actually the helium. And the helium is actually causing most of the pressure in this mixture, while the neon is not causing as much. And really the reason for that can be found right about here when we look at the molar masses of each of these gases. And in comparison, what we do see is helium is much lighter than neon. And because helium is much lighter than neon, it actually is going to be moving faster. It would have a faster velocity. And because it's moving faster, it's flying around faster, it probably would cause more collisions. And thus, that's why we see that it is the major contributor here between these two in terms of the pressures. So the mass of the gas, the molar mass of the gas, has an effect on how fast it's flying around or how slow, and the other way of looking at it is flying around. And thus, obviously, if it's flying around faster, you would expect more collisions. And if you're not flying around as fast, you would have less collisions. Any questions on that? Yeah, so the 0.0821, which is here, that's R. And R is a constant. Oops. So R is a constant, and you always have R, and R is up here. So it's obviously sometimes not given to you, but sometimes people will round R to this number as well. You can use either one. I personally use most of the time this number over here, but some people will round it, and occasionally I do as well. But R is always a constant. Oftentimes, like we talked about last time, they won't tell you R in the problem, so they won't say, hey, R is this. But if you kind of see yourself moving towards the ideal gas law, you should always just think in the back of your head that you always have sort of R available to you to use. Other questions? And R will always be that number, sort of no matter what the situation is. All right, let us take a look at some other situations. And just to let you know, I apologize, but I am getting a little kind of slowness when I write things. So that usually tells me that something not so good going on. So hopefully you can hear me. I apologize if I am cutting out or not. The good news is I think on the recording, it doesn't cut out or anything like that. I think it's just at some point, it's just there's too many people on, sort of, and it kind of gets a little tied up sometimes. So we'll continue on. If it gets really bad, let me know. We could kind of stop and restart, but hopefully it will sort of stabilize the audio and stuff like that. I think it's just some points I've had it last weeks or so during different times. It just sort of cuts in and out a little bit. I think it's just a lot of people on at once. All right. So another very common way that we can have a sort of partial pressure situation is a lot of times when we do gases and collect gases, sometimes the way that we collect gases creates sort of a partial pressure situation. And in that situation, what happens is, for example, here we have some potassium chlorate. And as we're heating this potassium chlorate, we're generating basically oxygen gas. And this oxygen gas is traveling through this tube and into this bottle. And this bottle eventually in it. And as the gas goes in, the water will go out. So the water will go out. And the result is you get this sort of empty area in this container. And this empty area really is not empty. It is the gas, and it has, for example, the oxygen gas, which you're interested in this case. But the process of doing this reaction as you're sort of heating this and you're collecting the gas over water is there's some heat that's associated, right, with this reaction. And the heat and water will also make you get water vapor, which is the gas version of water. So in this particular case, just as sort of the process or the procedure that you use to collect the gas, because you collected it with water, so sometimes it's mentioned collected over water, collected saturated with water vapor. These are keywords to let you know this is also a partial pressure type situation that's occurring. And usually you're not interested in the pressure of the water, so you're interested in just the pressure of the gas. So the pressure of the gas plus the pressure of the water vapor, and that's what that's usually referred to. The water vapor, usually you can look up on a table, and it's specific for a temperature. So you could look up on a table for the vapor pressure of water at a particular temperature. And usually what you can do is, because you're interested in the pressure of the gas, you can rearrange that and becomes almost like a subtraction problem. The pressure of the gas is the total pressure minus the pressure of the water vapor. And again, usually when you do this, you're interested in just the gas, which is the oxygen in this case of this example here. So you would take the total pressure. In a lab situation, the total pressure would be the barometer reading. So you would take a reading off the barometer that's hanging on the wall, and that would be your total pressure. And then the vapor pressure of water, you would look up on a table based on the temperature, and you would subtract it to. And sometimes that's referred to as getting the pressure of the dry gas. So you're sort of subtracting off the water, and you get the pressure of just the gas you're interested in. So this type of situation, whenever you collect the gas over water, or again, it's referred to as saturated with water vapor, that usually means you need to do this step here, where you're doing a simple sort of subtraction of the total pressure minus the vapor pressure of water. In a book type problem, they typically will give you the total pressure, but you may have to look up the vapor pressure of water. And usually in that gas chapter, there's usually a table that lists the vapor pressure of water for different temperatures. So as I mentioned, in this case, the water is sort of acting as the second gas that's there as a result of collecting it the way that the gas was collected. And again, we usually need to subtract off the water's contribution by looking up those values. So why don't you take a second here and try this one. The sample of oxygen gas is saturated with water vapor at 30 degrees. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of oxygen in atmospheres? So take a moment or two and give it a try, and then we'll talk about it. Okay, so let's take a look at this. So really the sort of keywords that you should look for when you see this is this part here. Whenever it says something like saturated with water vapor, or again, if it says collected over water, something to do with water, it will tell you that it is this type of problem that you usually have to correct for the water pressure or the vapor pressure of water. Again, the total pressure going to equal our pressure of our gas plus the pressure of water at that particular temperature. So in this particular case, they gave us the total pressure, which is 753, and they actually gave us the vapor pressure of water at 30 degrees Celsius, which is 31.824. The temperature actually in this case is not needed for the calculation. It's really just needed for you. If they did not give you this number over here, that you could go to the table and know you should look it up at 30 degrees Celsius. So really, this is just sort of a subtraction problem. So to find the pressure of oxygen in this case, we would take the total pressure, which was given to us, which again is the barometer reading when you do a actual experiment, minus the vapor pressure of water, which is a value that you could look up on the table, again for 30 degrees Celsius in this case. And that gives us the pressure of oxygen gas as 721 torr. And that would be the dry oxygen gas is sometimes referred to, again, because you subtract off the water. It did want it in atmospheres. So again, this is where that number that we saw earlier, the 760 number, is comes into play. So there are 760 torr in an atmosphere. So we would actually divide by 760, and that would get us a atmosphere of 0.949, which is the pressure of just the dry oxygen gas. Any questions on that there? So again, when you see this, it's sort of a partial pressure problem, and it usually occurs anytime the procedure where you collect the gas and water's involved. And again, in sort of a book problem, you want to look for those keywords like saturated with water vapor, collected over water, something to do with water will tell you that you usually have to do this subtraction part. If for some reason you need to use that pressure in an actual gas law, like the combined gas law, the ideal gas law, you would want to use the pressure at the end there, which is again the pressure of just the oxygen gas at where you've subtracted off the water. Any questions on partial pressures here? Okay, so just to wrap up sort of gases, this is the kinetic molecular theory of gases and some of the stuff that we talked about. First off, gases, they are tiny particles. They could be atoms, they could be molecules. Again, like helium, it could be an atom, molecule like oxygen gas, which is O2. Number two, the distances, the particles are small compared to the distances between them. So we assume that the volume of the gas is zero. And this is one thing that makes something an ideal gas law or an ideal gas is this idea that if you look back at a lot of the examples that we did, what you would see is a lot of times we don't necessarily talk about the volume of the gas itself. We oftentimes talk about the volume of the container that has the gas in it. And that's sort of an ideal situation that the gas is very small in terms of volume compared to the actual container it's flying around in. So we focus more on the volume of the container. The idea behind that is, again, the gas is flying around and it will fill the container uniformly. So we think about the whole volume of the container as being the volume of the gas in an ideal situation. Particles are constantly moving. Again, the collisions that occur with the gas is really what causes the pressure that we assert with gases. Again, more collisions, more pressure, and vice versa. Less collisions, less pressure. Number 4 as well is something that makes something an ideal gas, which is number 4. And in an ideal gas situation, in addition to assuming that the gas has sort of no volume itself, we also assume that there is no attractive forces or repulsive forces that occur between different gas molecules. And the main place where we sort of see that effect in an ideal gas situation is what we were just talking about in a situation when we have a mixture of gases. So if you remember what we just did in sort of that mixture of gases is, although we had a container that contained different types of gases flying around, we were able to do the calculation for each gas individually, like they were in there by themselves. And in an ideal situation, that's sort of what we assume. We assume that although there's a mixture of gases and there's different gases basically in there, there's really no attractive forces or repulsion forces between the different gas molecules. And that can affect, pressure when we sort of think about that. So for example, if we just simply had a wall of the container and we had this gas molecule here heading towards it, and we had another gas molecule behind it. Ideal situation, this gas molecule is basically free to slam into that wall, sort of as fast as it can or as hard as it can with no effect because there's somebody else there. But if there was, for example, an attractive force between these two guys, so there was some type of attraction force between those two gas molecules, what would happen potentially is that gas molecule would no longer be free to sort of slam right into that wall. It would kind of be pulled back a little bit because it's attracted to that gas molecule. Or vice versa, if there was a repulsion force, it would kind of go away from the gas molecule quicker. But since there is no sort of attractive force or repulsion force, we feel even though that they are mixtures of gases, they're in there kind of separately. They can basically fly around freely. One gas molecule being in there with it will have no effect on another. And for our class, that's pretty much what we deal with, which is ideal gases. Everything you could assume is an ideal gas. There are gases which really don't behave that way, and those are referred to as real gases. And we don't talk about real gases till maybe you take the next class, 1A, I think they call it here. So if you take 1A, for example, you would talk about real gases. And under certain situations of pressure and temperature, the ideal behavior basically doesn't hold up. So we get sort of a real gas situations. But for the most part, you can usually assume ideal gas situations. And really, number 2 and number 4 on this list are the ones that sort of make a gas an ideal gas. The last one on the list there is the kinetic energy of gas molecules is proportional to the Kelvin temperature. So that has to do with the idea we talked about that. For example, if you raise the temperature, we would expect our gas molecules to fly around faster. And if you lowered the temperature, they would lose some energy and they would not fly around as fast. So you should be familiar with the 5 sort of points of the kinetic molecular theory of gases and sort of the 2 guys that sort of make something an ideal gas. Any questions on that? And we'll just go through these. These are just some of the relationships that we talked about as we went through the different gas laws. So temperature is a measure of the motion of gases. So as we just talked about, if we sort of increase the temperature, we would expect those gas molecules to be flying around faster. That should increase the rate of collisions, and thus we probably should see an increase in pressure, especially if the volume does not move, and vice versa. If we lower the temperature, everybody should be flying around slower, which means that we should have probably less collisions. And again, if the volume doesn't adjust, it should decrease the pressure. The pressure and temperature in a rigid container, which is really our Guy-Lussac's law, that's our one that we saw earlier, our kind of P1 over T1 equals P2 over T2. And again, in this case where the volume is held constant, if we do increase the temperature, again, the volume will not adjust. So we would expect an increase in the pressure because of the increase in the rate of collisions, and vice versa. If we decrease the temperature, we would expect less collisions and we would expect the pressure to go down. The last one is sort of Charles law relationship, which is our V1 over T1 equals V2 over T2. This is at constant pressure. And this is the one where it will adjust the volume to keep the pressure constant. Again, if the temperature goes up, so will the volume. And again, the volume needs to adjust to allow the temperature, to allow the pressure to remain constant. And vice versa, if we lower the temperature to avoid the pressure dropping, what happens is our volume will decrease to basically keep the rate of collisions the same. And we would expect the pressure again to remain constant. So these are a lot of sort of the relationships that we talked about earlier on in this chapter in terms of those gas laws. Any question on gases, gas laws? So a reminder, you do need to know the different gas laws. They will not be provided for you. Obviously, you need to be able to solve for any of those variables. You need to be able to do partial pressure problems. And obviously know how to convert between probably millimeters of mercury, torr, and atmospheres, which is that 760 number. Any questions on gases before we change gears a little bit, I think? Okay. So the next thing that we're going to talk about is some forces that hold, for example, molecules together. And there's two types of sort of forces that we talk about when we talk about molecules, and how molecules interact with other molecules and how they're sort of held together. So the first one was sometimes referred to as an intermolecular force. And an intermolecular force is the force that holds two molecules together. So two whole molecules together. And that in this case is the force between this water molecule on the left and this water molecule on the right. And if you remember, water is polar. So water has a negative side on the oxygen. It has a positive side on the hydrogen. And that allows them to interact with each other through this right here, which, as we will see in a second, is known as hydrogen bonding. And that sort of positive negative attraction that occurs between different molecules is the one where we know as an intermolecular force. Now, intramolecular force, so an intramolecular force, intra means within the molecule. It is within the molecule that holds one molecule together. So as you can see here, that would be something like the bonds that we see between the oxygen and hydrogen in that one molecule of water and the oxygen and hydrogen bond in that one molecule of water as well. So that's like your electrostatic attraction that we see in ionic compounds. That's your covalent bonding that we see in molecular compounds where they share electrons. Now, between intramolecular force and intermolecular force, the one that is stronger is always the intramolecular force. So the intramolecular force is always the strongest between, again, intramolecular and intermolecular forces. And we know that from a very simple example of that. If you take some water and you put it on the stove, you're going to make some pasta. When you start to heat the water, the first bond that breaks happens at its boiling point, and the first bond that breaks is actually between liquid water molecules and liquid water molecules. And what we end up getting basically is separate water molecules that occur. We get steam in that case, which is basically just water in the gas phase. It would be different if it was opposite, if the intramolecular force was weaker than the intermolecular force. Then what would happen is, as we would heat something like liquid water, the bonds that would break would be like between these guys, the hydrogen and the oxygen, which would not be good, because then you would generate hydrogen gas and oxygen gas, and you probably would not get to the actual pasta making part, because that probably would explode and stuff like that. So always an intramolecular force, which is basically the bonds within a single molecule, is basically always stronger than any intermolecular force, which is the bond between one molecule and another. Otherwise, again, as you would start heating things, you'd get alphabet soup, basically. So we're going to talk about some different types of intermolecular forces. So intermolecular forces, again, are these forces that hold one entire molecule together with another entire molecule. Could be the molecule itself. It could be with another molecule that's just like it. It could be one molecule with a different molecule. But again, the whole molecules together, held together by these intermolecular forces. So the first type of intermolecular force occurs when we have what is referred to as dipole-dipole interaction. Dipole-dipole interaction, if you remember, dipole we heard about when we were talking about bonding, and those are usually a result of polar molecules. So we got one polar molecule that has a positive and negative side. We have another polar molecule that has a positive and negative side. And that's basically what polar means. Polar means that you have an unequal sharing of electrons. And in a molecule, that means as a whole, that molecule has unequal sharing of electrons and creates a positive side and negative side. And because these molecules have a positive and negative side, that is what gives them a way to be attracted to each other. And it gives them a way to basically bond with each other. The positive side of one polar molecule will be attracted to the negative side of another polar molecule. And again, that positive negative attraction, which is ultimately what all these intermolecular forces are, is basically the idea of positive side, negative side attracted to each other, is what holds that together. So dipole-dipole is essentially the intermolecular force that is responsible for holding one polar molecule together with another polar molecule. It's only about 1% as strong as covalent or ionic bonding. Again, covalent bonding and ionic bonding, those are intramolecular forces. So as we were just talking about, those intramolecular forces are always much stronger, but this is a relatively strong intermolecular force, this dipole-dipole. And again, it is the main force that holds one polar molecule together with another. It does become weaker as the distances between the molecules get longer. So it's like stretching out sort of a rubber band. At some point, if you stretch it too far, it's just going to kind of snap apart from each other or snap back, and that's sort of the idea there as well. Now, there is a certain type of dipole-dipole interaction which gets its own classification, and that is what is known as hydrogen bonding. And hydrogen bonding is a very strong dipole-dipole that it's classified as almost its own intermolecular force. And it occurs with a bond between hydrogen and nitrogen, oxygen, and fluorine. So that's an important part to understand, is in order to have hydrogen bonding being able to occur, you do need to have a bond between hydrogen, that's between hydrogen and either nitrogen, oxygen, or fluorine in a particular molecule. And if you look at the periodic table, those three guys, the nitrogen, the oxygen, and the fluorine, they're all right up here, top right of the periodic table. And if you remember about electronegativity, which is that ability of an atom to bring electrons towards itself, increases on the periodic table as you go up and to the right. So this creates a very polar bond between hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. And water is an example of this. When we look at water, again, the oxygen is more negative. The hydrogen side is more positive. And when two water molecules come together, the negative side of one is attracted to the positive side of another, and we have a hydrogen bond situation occurring. So hydrogen bonding is the force that occurs between hydrogen and some electronegative atom between nitrogen, oxygen, and fluorine. Now, again, it's important because when you look at something, for example, if I look at CH4, you may say to yourself, well, CH4 has got a ton of hydrogens. It should be able to hydrogen bond. And actually, CH4 cannot hydrogen bond. So it cannot hydrogen bond, even though it has a bunch of hydrogens there. And that's because if you remember, the bond between carbon and hydrogen is a non-polar bond, which means there's no separation of charge. It's kind of neutral if you want to think about it. And it has no way to do that sort of positive negative attraction. So although it has a bunch of hydrogens, it lacks that ability to hydrogen bond. So usually we'll see hydrogen bonding in things that are polar, and it definitely needs to contain a hydrogen bonded to either a nitrogen, oxygen, or a fluorine in that particular case. The last type of intermolecular forces is ones that are known as dispersion forces. And dispersion forces are the weakest of all intermolecular forces. They are the forces that hold together kind of non-polar molecules. So for example, if I had two non-polar molecules, very badly drawn, remember that a non-polar molecule basically is neutral. It has no positive side, no negative side. So they really don't have any way to interact with each other. But remember that, this molecule here on the left has electrons that are moving around. So it's that all the electrons decide, hey, I'm just going to go to the right-hand side here. And if all the electrons decided temporarily to move to the right-hand side of that molecule, this guy that normally does not have a charge on the left-hand side will gain a temporary charge because those electrons, for example, just moved around. And the effect of that is if he's standing still next to another nonpolar molecule, because these electrons are here on this side of the molecule on the left, the electrons in this molecule will decide, I need to get away from you, because remember, things that have the same charge don't want to be next to each other. And what happens in that case is now we end up with our first molecule that gained a temporary positive negative side. Our second molecule will also now gain a temporary sort of positive and negative side. And these two nonpolar molecules that started out with really no charge have now temporarily gained a charge. And that does give them a place where they can now interact with each other through that positive and negative attraction. And that is what is known as dispersion forces. And they're relatively weak because as soon as the electrons sort of move back to the kind of their normal position, this bond will break apart and new ones will form and will break apart and new ones will form and break apart. The strength of dispersion forces increases with molecular mass. So the larger the molecule, the more electrons it would have. There's a greater chance of those electrons moving around and creating these sort of temporary attractive forces. So to sort of summarize these three different sort of intermolecular forces, and in terms of their strength, just find this place to scribble here, maybe. I'll just do it here. So to sort of summarize, the strongest of all three of those intermolecular forces is hydrogen bonding. And hydrogen bonding is for polar molecules, and polar molecules, they could come together that have the ability to hydrogen bond. The next strongest is dipole-dipole. Also for polar molecules coming together with polar molecules that do ability to hydrogen bond. And the weakest of all of them are dispersion forces. And so again, the strongest is our hydrogen bonding. So in reality, every single molecule to some extent can do dispersion forces. But most of the time, we reserve sort of dispersion forces as the major force that holds one nonpolar molecule together with another. While dipole-dipole, again, is typically for polar molecules interacting with other polar molecules. And the idea there is they lack the ability to hydrogen bond. And our hydrogen bonding is reserved for polar guys that have the ability to hydrogen bond. So for example, we had water. We had NH3. We had our this guy here. We had the guy that we had before. So in this case here, our water molecules have the ability to hydrogen bond. Our NH3 here would also have the ability to hydrogen bond. It has a bond between nitrogen and hydrogen. This is also a polar molecule. Although it does have a hydrogen, that hydrogen is going to be nonpolar. It does not have the ability to hydrogen bond. So this is something like dipole-dipole. And lastly here are carbon hydrogens. That's all nonpolar, which means that this would use dispersion forces as its main force. So sometimes if you're not sure, quickly sketching the Lewis structure will sometimes help you identify whether or not perhaps the molecule is polar or nonpolar, has the ability to hydrogen bond or not hydrogen bond, by just kind of quickly drawing that Lewis structure, thinking about what we talked about when we talked about bonding, symmetrical, unsymmetrical geometries. So typically something that's going to be polar would have one of those unsymmetrical geometries and be able to hydrogen bond if it does have a hydrogen contained to a nitrogen, oxygen, or a fluorine. Or if it doesn't, it'll be able to do dipole-dipole. The difference between sort of dipole-dipole and dispersion forces, although they both may look the same, that they both have a positive negative side, the major difference really between sort of these two guys here is in a dipole-dipole situation, it's usually involving a polar molecule. And what that means is no matter what the situation, if you have a polar molecule, there's always going to be a positive side and a negative side. And it will never go away. It's always going to be kind of fixed that way, positive, negative side. The difference between that and something that's non-polar is most of the time, a non-polar molecule will look something like this. It will essentially have equal sharing of electrons. It won't have a positive or negative side. And it's only when it temporarily gains that positive negative side that it's able to interact. And that's why it's a very weak intermolecular force, dispersion forces, in a non-polar molecule, because most of the time they don't have that sort of separation of charge, as opposed to a polar molecule like on the very top there. No matter what the situation is, it's always moving around with a side that's more positive and a side that's more negative. When we do get these guys together, which is what this picture here shows before I started scribbling on it, is when they do come together, obviously no matter what you do, there is going to be a positive guy near a positive end or a negative end near a negative end. And what will typically happen with molecules is as they come together, they will sort of try to move around in such a way that they maximize the attractive forces between one molecule and another and minimize the repulsion forces that occur. And here's some examples of hydrogen bonding between water molecules. Again, the positive side of one water molecule attracted to the, the negative side of another. And again, they just keep kind of hydrogen bonding all around. Again, this is going to be a very strong intermolecular force, the strongest of those three. Again, a bond between hydrogen and oxygen. It's very electronegative and very strong attractive force. This again is sort of our dispersion forces, is sometimes what it's referred to as a instantaneous dipole, because these polar molecules normally don't have any type of separation of charge like you can see on the left. They're kind of neutral if you want to think about it that way. Again, as those electrons have the ability to sort of move around and they all vacation to one side of the molecule versus another, it temporarily creates two molecules on the right-hand side that have charges. So we have this guy, which is our positively charged, this side, which is negatively charged, and that gives them a place to basically interact with each other. That little symbol there, again, as a reminder, is the delta positive and delta negative, which means partially positive and partially negative charge of that molecule. Again, as those electrons move back to their normal location, they will kind of break apart and form new ones. And again, that's why it is very, very temporary, because although on the right-hand side, they do have a partially negative charge and a partially positive charge, at some point, those electrons will go back to kind of their normal way, and that molecule will return to this more neutral environment. And that, again, that does not occur with a polar molecule, because no matter what the situation, those electrons aren't going to move back from one side to the next. Any questions on intermolecular forces? Okay, so the last thing we're going to sort of talk about here in this chapter is specific heat. And there is an equation that goes with specific heat. And the equation is Q is equal to ms delta T. The specific heat, or specific heat capacity, it is sometimes referred to as specific heat capacity, is the amount of energy that's required basically to raise 1 gram of a substance by 1 degree Celsius. And energy, two common uses of energy that we see with specific heat are these guys. It's calories with a lower c and joules, capital J, and CAL obviously as calorie. sort of abbreviation. There's 4.184 joules in a calorie. And that's a conversion that's used a lot to convert between joules and calories. And when we look at this equation here, Q is heat, or energy. And again, it has units of joules or calories. M is hang on a sec. Good thing they invented erasers, I suppose, right? So our change in temperature, let's try that again here. Come on. There we go. Change in temperature is our final temperature minus our initial temperature. And oddly, I know we just talked about gases and gas laws and temperature needing to be in Kelvin. When you use the specific heat equation, typically you can leave the temperature in degrees Celsius. So, and that is because when we talk about S in this case, which is the specific heat capacity, it will have units of either calories per gram per degree Celsius, or it will be joules per gram per degree Celsius. So these are two common sort of units. And again, you can see the temperature in both is degrees Celsius, so you can leave it in that. Now, specific heat capacity is sometimes abbreviated S in a formula. Sometimes people will use SH. And sometimes people may even use C to describe specific heat capacity. And that's basically what these units represent, is the definition of specific heat capacity. It's the amount of heat or energy, which is joules, that's needed to raise 1 gram of a substance by 1 degree Celsius. So this value is typically a value that you can look up in a table. It is different for different substances, depending on their state. And so you can even have the same substance, but if it's in the solid, liquid, or gas state, you will have different numbers. For liquid water, the specific heat capacity is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. As you might expect, that is kind of where we get this conversion factor from. So the specific heat of liquid water has a value of basically 4.184 joules per gram per degree Celsius. Just to illustrate the difference, if I took, for example, off the top of my head, if I took water in the solid state, the specific heat capacity for water in the solid state, or ice, which is what that is actually something like 2 joules per gram per degree Celsius. So it is a different number, and the state is really important. So we'll see a specific heat capacity table in a bit. When you look at that table, you want to make sure you look for what you're looking for in terms of the substance, but just as important, you want to make sure you look up the value for the correct state. Is it solid, liquid, gas? You want to make sure you get the right one. The larger the specific heat capacity, the less its temperature will change when it absorbs a particular amount of heat or energy. So what that means is if something has a specific heat capacity that's really large, it takes a lot more energy to change the temperature of that substance than something that has a smaller specific heat capacity. So for example, if something had a specific heat capacity of 0.5 joules per gram per degree Celsius versus something like water, 4.184 joules per gram per degree Celsius. And comparing these two guys in terms of their specific heat capacities, you would see this guy start to change temperature a little bit quicker, because again, it only takes 0.5 joules of energy to change the temperature of 1 gram of that by 1 degree Celsius. Where, for example, for our water, you would have to put in 8 times the energy to get the same gram of water to change that temperature by 1 degree Celsius. So the higher specific heat capacity, the more energy you would have to put in there to get it to actually change temperature. The lower the specific heat capacity, the less energy you would have to put in there. That's why, as a whole, when we think about water and we think about sort of changing the temperature of water, the water takes a lot of energy to do that. And that's why when we talk about, say, something like global warming or something like that, when we talk about the water and the ocean's temperatures changing, because there's so much water in there, and obviously it takes an incredible amount of heat just to move the temperature by 1 degree Celsius. And that's why it's significant sometimes when it does move by just, say 1 degree Celsius, because that means that's a lot of energy needed to do that. And here is a table of some specific heat capacities, both in calories per gram per degree Celsius and joules per gram per degree Celsius. This is found in your book, I believe, as well. So you can see that if we look on here, water, as I was just mentioning, you have some different values. Again, these are all water, but they are in different states. Liquid water, that is basically steam, right? This is ice, right, which is the solid version of water. And you can see that they do have different values for the specific heat capacity. So again, it's really important if you go to a table like this and you look up the value, that you, again, do not just take the first one that you see. You make sure that it is in the right state, again, because they will have different values. So let's take a look at an example of calculating specific heat. We want to know how many calories are needed to heat a pot of 1,600 grams of water from 25 degrees Celsius to 100 degrees Celsius, right? So we could use our specific heat equation, which is Q is equal to ms delta T. And we're looking for how many calories, which is really heat. Remember, heat is either joules or calories. Needed to take 1,600 grams of water. So that is the mass, 1,600 grams. So we have this number. We're going from an initial temperature of 25 degrees Celsius to a final temperature of 100 degrees Celsius. 1,000. Come on, stay with us for just a little bit more. And that basically is our change in temperature. Now, the specific heat capacity here, we're talking about liquid water, because remember, the boiling point of water is 100 degrees Celsius. So it's still liquid water all the way through here. From here to here, it's all liquid. And again, that comes from that table. So we can put our numbers in. We would get Q is equal to our M, which is 1,600. And if we do all that, we get 100 minus 25. We're going to times it by 1. We're going to times it by 1,600. We're going to end up with 12, 1, oops, 2, 3, 4. The units are joules. Degrees Celsius cancel. Grams cancel. The units are actually calories. My bad. I'm sorry. Calories. Now, if you wanted it in joules, you could just do the conversion, or you could actually put the numbers in and just use the specific heat in joules. Again, it didn't ask for joules in this case. It would look exactly the same. And again, if you did it in joules, you would get something like 502,080 joules. We'll forget sig figs for the time being since we're getting to the end. And again, you could also have just taken your 12 0.0000 and times 4.184 and times it by 4.184. So you could have just done the conversion times 4.184 joules is a calorie. And you'll get down to here. So you could have done it either way, just put it in there. But what does this number mean, just to kind of finish up for today? What does this number mean? This number is, again, the energy that is needed. When we calculate something like Q, we can determine what type of reaction is happening. If Q is a positive number, that means it's endothermic and heat and energy is absorbed. And if you calculate Q and it's a negative number, that means that this reaction is exothermic and heat and energy is released. So what we see here is, in this particular case, this is an endothermic process, which would make sense because if you put a pot on the stove, you have to put the fire underneath it, and that water is gaining all that energy, which means it's an endothermic process. And we see that with both of our numbers that we got here. This guy is a positive number, and this guy is a positive number, no matter if you did it in calories or joules, and that would tell you that it is a endothermic process. And what really will determine whether or not you'll get a positive or negative number when you look at the specific heat equation, Q equals delta T, it is the change in temperature part, the final minus the initial. And that's why it's really important when you do these problems to actually do the final minus the initial, because that's ultimately what's going to give you your negative or positive number for Q. And that will tell you whether or not it'll be endothermic or exothermic. So if I did the opposite of this, if I took water at 100 degrees and I cooled it down to 25 degrees, the only difference in this calculation would be that my final temperature would be 25 and my initial temperature would be 100. And that would give me minus 75 degrees Celsius. And that minus would translate to a negative Q value. And that would make sense, right? If you're cooling down, say, water from 100 degrees to 25 degrees, which is the opposite of this question, you have to release heat and energy. When you release heat and energy, that's exothermic, and we would expect a negative number. So I think it's really important to make sure you do final minus initial in terms of temperature. That gives you the correct sign in terms of exothermic or endothermic. In reality, if you did just larger number minus smaller number, you'll get the same value, but you won't have the benefit of negative or positive. Any questions on that? So we're nearing the end of this chapter. So next time we will continue and finish chapter 7. We'll roll into chapter 8. And those notes are already up there on Canvas if you need them. And other than that, have a good rest of your day. And I'm almost done with your exam, so I'll have those for you in the next day or two, your results and stuff like that. All right. Have a good rest of the day. I'll see you on Wednesday. Thank you. Thank you. You too.